Hari Om. In this video, we discuss with the motional EMF. Motional EMF is related with when we move a conductor through a magnetic field. Across the ends of the conductor, an EMF is induced, and that through motion the EMF is obtained. That is called motional EMF. Now here I consider a uniform magnetic field B, which is pointing into the plane of the ball as shown. And I move a conductor of length L with a velocity v along this particular direction. Now as the conductor moves along this particular direction, it will be cutting the magnetic field lines. So there will be a change of flux coming, and that will be inducing an EMF in the conductor. Now let us assume how this EMF is being developed. Now when I move the conductor along this particular direction, see, the conductor will be having enough free electrons there in the body of the conductor. Those free electrons are also moving with the velocity v. So if I take one such electron and that electron is moving along this direction with velocity v in a magnetic field, there will be definitely a magnetic Lorentz force is acting on it. And that magnetic Lorentz force direction will be obtained by applying Fleming's left-hand rule. And if I apply the left-hand rule here, magnetic field is into the plane, movement of negative charge. So I will be taking it in the opposite direction, and the force will be acting downward. That means the free electrons will be moving downward. All the free electrons will be moving downward, and effectively those electrons will be concentrating at this end, and this becomes more negative. So this end becomes more negative and this end will be less negative. Therefore, this can be considered as positive end. So as we move the conductor, this end is acting as positive and this end acts as negative. So across those two ends, there will be an EMF developed which is of this type. Understood? Now, if I connect this with an external circuitry, if I connect this with an external circuitry, like if I complete the circuit like that, this end is positive, this end is negative, so the current will be flowing in this particular direction to complete it. So through the conductor it moves from negative to positive, the current flow. So induced current will be flowing in this way if you complete the circuit across the conductor. Now this direction of flow of induced current can be identified with Fleming's right-hand rule. Fleming's right-hand rule, if I hold the right hand three fingers, that is middle finger, forefinger and the thumb in mutually perpendicular direction, in such a way that forefinger shows the direction of the magnetic field, thumb shows the direction in which the conductor is being moved, then the middle finger shows the direction in which the induced current is flowing. Now let us see how this is possible here. So this is the direction of the magnetic field. This is the direction in which the conductor is being moved. Then the direction of flow of current is upward. So this is what we identify as per the basic theory, but Fleming's left-hand rule also tells the same thing. So you can identify the flow of induced current using Fleming's right-hand rule. Okay? So you understood how this induction is taking place. Now, what is the equation for induced EMF? Let us see from this itself. To find the induced EMF, let us take the Faraday's laws here again. Now, as you move the conductor along this direction, let us say through a distance x. If I move up to this, the conductor is moved up to this, suppose. Then, if the conductor is moved through a distance x, then it defines an area here, and that area, let us assume A, imaginary area within which the magnetic field lines are cut by the conductor. Let it be A. Then what happens is that, as per the Faraday's laws, we can have induced EMF is equal to minus d phi by dt. But here, the phi will be equal to B dot A. That phi is equal to B into L into X, I could say. And this is exactly perpendicular to the field lines, therefore, dot product will be maximum. You get it like this. And therefore, if I put that over here, you get induced EMF E is equal to minus of d by dt of B into L into X. But we know that B and L are constant over here, and X is the only variable. Therefore, I can write this as induced EMF is equal to minus of B into L into d by dt of X. But d by dt of X is nothing but the uniform velocity v with which you are moving it, and therefore you can have induced EMF E is equal to minus B into L into B. This is the equation for motional EMF here. Okay? But here we have taken the special case that it is exactly vertical here. But sometimes the alignment of the conductor will not be perpendicular if I say if this is the field line, and suppose this is the way the conductor is staying in the field, then this will be making an angle theta here. So if this is the case, then induced EMF E will be equal to minus B into L into B sin theta. And this sin theta is obtained from Lorentz magnetic force. And you can find that if this conductor is aligning parallel to the field, induced EMF is 0 because there is no flux linkages coming. And if it is exactly vertical like this, then there will be maximum induced EMF is coming. So this is what we can say about motional EMF.